Hello, Algebra students. This lesson is on graphing the standard form. In the previous lesson, we were looking at graphing from factored form, and so this is the second half of our learning how to graph quadratic equations lessons. To get us ready for our lesson today, please try the warm-up question on screen. The warm-up question is not about quadratics, but it'll give you an idea of what the lesson today is going to be all about. Go ahead, pause the video, try it now, and then come back when you have an answer. So the warm-up question is asking you to match these three graphed lines, A, B, and C, with these three equations. The idea of this is that there are multiple things we can use to help us identify these graphs from these equations. For example, one of the things I can look at from these equations and identify is the slope of each line. Slope tells you the direction of the line. So for example, the slope of this line is 2, the slope of this line is -1, and the slope of this line is 3. Just by knowing that y equals 3 minus x has a negative slope, that lets me know already which of the lines down here it is. A negative slope means the line is going down from left to right, and so that must be equation A, y equals 3 minus x. When we learned about linear equations, we also learned a bigger slope, like 3, is going to be steeper or more vertical, more up and down, than a smaller slope of 2. So even though both of those are positive slopes and they're both going up, just because that 3 is bigger than 2, I know it's steeper. That means it's going to be more up and down than a slope of 2. So using that, I can identify that graph C is going to be the steeper slope, and graph C is going to be y equals 3x minus 2, which leaves me with B is going to be y equals 2x plus 4. I could also go in and identify specific points and use those points and rise over run to help me confirm that the slopes are 2 and 3 of those two lines. There's a different way you could have done this, though. Instead of looking at slope, you could also have looked at the y-intercepts. We have a y-intercept of 4, a y-intercept of 3, and a y-intercept of -2. Just by knowing, for example, that last equation has a negative y-intercept is going to mean it's the only line crossing our y-axis below 0. And that's another way I could have figured out that y equals 3x minus 2 goes with that blue line. The blue line is the only line that crosses our y-axis below that origin point. And similarly, a y-intercept of 3 and 4. 4 is the biggest y-intercept, so I know it must be the highest on our y-axis. And so that leaves me to conclude it's the green line, and so on. The idea of this is that when you have linear equations, there are multiple characteristics we can identify about the graph looking at those equations. Here, specifically, it was slope and y-intercept. What we're doing today is the same idea. We're just going to be looking at quadratic equations and coming to these same conclusions. When you look at a quadratic equation in standard form, there's a couple different things you can know about the graph if you know what to look for. And that is what we're doing today. The goal of this lesson is right here. It says I can explain how the A and C in our formula for standard form affect the graph of the equation. A is the number in front of the x squared, and C is that constant, that number by itself, like plus 3, plus 5, that we sometimes see in the equation as well. And then the second part of this lesson is going to be connecting a lot of different things we've learned in the past 3 lessons about graphs of quadratics and how those all are related to each other, how we can connect all of those together. For the first part of this lesson, which we're calling Quadratic Graphs Galore, we are going to use graphing technology, specifically this website called Desmos, to help us graph these quadratics. We're going to start off with the graph of y equals x squared. That is like the most simplest quadratic graph you can see. We said all quadratic equations have x squared, and most of the ones we've been looking at have other terms, but just y equals x squared, that's the most basic quadratic, and we're going to use that as our starting point. And then we're going to make some changes to that function, to that equation. For example, the first change we're going to make is adding different constant terms to it. So stuff like x squared plus 5, x squared plus 10, x squared minus 3. And we're going to watch the graph and see how it changes. We'll do a couple of these, and while you're watching those changes that happen when you add a constant, the goal is to identify how it changes our graph. So starting with this, I'm going to move us over to that Desmos website. And like I said, we're going to start off with the graph y equals x squared. Y equals x squared is this red line right here. Notice it's some of the stuff we've said. It's a quadratic graph, so we've got that parabola there, that U-shaped curve. And then from this as my starting point, I'm going to change this equation by adding some constants. So ready? So I'm going to start by adding 3. Notice how the graph changed. I'm going to add a 5. Again, notice how the graph changed. And I can even zoom out more so you can see it. And then let's do one more. I'm going to do subtracting a 10. And again, notice how the graph changed. Do you see what putting a constant here does to the graph? When I've taught this in person, some students have noticed that the vertex, that bottom point on our graph, is moving. They said that, for example, when it's negative 10, I can see that vertex is here on my y-axis at negative 10. When we've got 3, I'm seeing it's here, the y-intercept is at 3. And we see that it's changing where it is on our y-axis. I'm going to do one more. I'm going to do x squared plus, let's do 5x plus 3. Here now, there's only one point that is at the 3, and that is our y-intercept. The vertex is down here. So what I did here was I made the vertex and our y-intercept different points. Earlier, they kept being the same, like this. But we're seeing that constant number is the y-intercept. We actually noticed that 2 lessons ago, but since we're talking about standard form again, this is a good reminder. That constant will always be your y-intercept. So let's go ahead and summarize that in our first part. It says, adding different constant terms to x squared. I would write those exact words in my notes and then finish it with changes the y-intercept. For me, I always think of myself as a visual person, so I like having pictures in my notes as well. And so the other part I would include in my notes is a picture of what we were seeing. I'm going to go ahead and put that y equals x squared, since that was our starting point. So that green line is my y equals x squared. I'm going to use a different color and show that when we change that to y equals x squared plus 3, for example, it moved, that's a little not balanced, but it moved our parabola up. If my equation was y equals x squared plus 3, it made that y-intercept here at the number 3. For me, this is what I would want in my notes. And this is the first of 4 observations we are going to make. This was talking about the constant, or that c in ax squared plus bx plus c. The last 3 of these are going to be about what happens when you change the number in front of x squared, when you change that a term in ax squared plus bx plus c. So coming down to the next one. The next thing we're going to look at is what happens when you multiply x squared by positive coefficients greater than 1. So by positive numbers bigger than 1, like 3x squared, 7.5x squared, etc. So we're going to do the same thing. We're going to come back to our Desmos graph. I'm going to get us back to our y equals x squared. I'm actually going to leave this here just so it makes it easier for us to see what's happening. And I'm going to graph our new equations down here. So again, I've got my y equals x squared. And we're going to go ahead and put numbers bigger than 1 in front of our x squared. So for example, here is 3x squared. Just to make sure we understand what we're looking at. The red line is our starting point. Y equals x squared, and then y equals 3x squared is that blue line. Let's do a couple more. That's y equals 3x squared. This is y equals 5x squared, y equals 10x squared, and y equals 13.4 x squared. Again, do you see what is happening to our graph and our parabola as I put numbers greater than 1 in front of x squared? Well, notice here are where the sides of the parabola were originally. And as I was putting all of those bigger positive numbers in front of x squared, the sides of my parabola were moving. My y-intercept is still here at 0. That should make sense because the constant for both of these is 0. I don't see plus or minus a number, but the sides of the parabola are moving in. Lots of times we describe that as the parabola is getting more narrow. The two sides of the parabola are getting closer together. I've also had people talk about it being like skinnier, but the most common way you hear that described is our parabola is getting more narrow. And notice when I pick even bigger numbers, it makes our parabola even more narrow. So for example, this is 3x squared. This is 30x squared. That's a bigger number and it got even skinnier. This is a 300x squared. I chose a really big number and it got really, 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 really narrow. If I pick even a bigger number, oh my goodness, those sides are so close it almost looks like they're touching. They're not, but it almost looks like they are. And so we see the bigger the number is that you're multiplying it by, the more narrow it gets. And so that is what I would put in my notes for the second observation. I would write these words again. Multiplying x squared by different positive coefficients greater than 1 is going to makes our parabola more narrow. And so again, I like to include pictures in my notes as well. So I'm going to do the same thing. I'm going to use one color to show that parabola we were starting with. I'm going to use one color to show y equals x squared. And then I'm going to pick a different color to show what happens when we pick a positive coefficient greater than 1. So I'm going to do this example one, the 3x squared. And if you do a number greater than 1 that's positive, it makes it even skinnier. Those two sides are coming closer together. And so that is my y equals, oops, I need a 3. That is our y equals 3x squared. And so this is what I would include in my notes for the second part here. We've done 2 observations. We got 2 more to go. The next one is what happens if we multiply it by negative numbers, less than -1. So when we say less than -1, it's numbers that are bigger than 1, like 2, 3, 4, 5, 6. It's just negative. So -4, -3, -10, -100. We're going to make that same observation. What happens? This is similar to what we did earlier. I'm just looking at what happens if those numbers are negative. So again, I'm going to keep my y equals x squared right here. And then let's play around with some negative numbers. So for example, I'm just going to start with y equals -3x squared. And that is this green parabola down here. We'll do a couple more. Y equals -7x squared. And y equals -20x squared. For me, I think this is the easiest one to see what happened. Do you see what happened to our parabola? It flips upside down. And all the same things we had said earlier are true. When I was picking bigger numbers like 25, 100, it's making it narrow again. That negative sign just means it's going down instead of up. If I take that first parabola and I make it a 20x squared, it's real easy to see. They're both the same width. They're both really narrow. That negative sign has just made it face down. And those words face down or face downward are how we describe it. So for this third observation in our notes, I would put multiplying x squared by negative numbers makes the parabola face downward. When we say face downward, that's the official way you would hear it described. Similarly, I'm going to write this positive coefficients face upwards. We use those words face downwards and face upwards. I would know what you mean, though, if you say the parabola goes up or down, but these are the words you hear a lot. And so when we say face downward, I'm going to draw 2 graphs again. So face upwards are our positive ones. So for example, something like this would be a positive number like y equals x squared. That's a positive one. But if I have a negative number in front, it's going to face downwards. I made those the same width. This is just going to be my negative x squared there. And so those are our two examples. There's one final observation to make. We've talked about numbers bigger than 1, like 3, 4, 7.5, 20. Let's look at those numbers smaller than 1. And so that's this last part. We're going to look at numbers smaller than 1 that are positive and negative. So for example, 1/2 x squared, negative 0.25 x squared. And one last time, we're going to check and see what's going on with our graph when we do that. So one final time, I'm going to leave my y equals x squared right here as our starting point, and let's pick some smaller numbers. So for example, y equals 1/2 x squared. That is this like bluish purplish line right here. And we'll do a couple more. Let's do y equals 0.3 x squared. That's this one. Let's see what happens if it makes it negative. Okay. And let's do maybe one more, 0.1 x squared. Do you see how our parabola is changing? It's the opposite of what we noticed before. When we were picking larger numbers, like 5, it was making it skinnier. It was making it more narrow. When we pick numbers smaller than 1, like 0.1, it makes it wider. The two sides of my parabola are moving further apart from each other. And it's the same way we described it earlier, but opposite. The smaller the number, the wider it gets. So notice 0.3, 0.2, 0.1. See how the sides are moving away? Can you think of a number smaller than 0.1? Well, what about 0.01? Oops, I can't put two decimals up. There it is. It's a very wide parabola. Those sides are really, really far apart from each other. And so that is our final observation. So one last time in our notes, we're going to say multiplying x squared by different coefficients between -1 and 1 makes the parabola wider. And so for my picture, I might show that if y equals x squared is this blue line, that's my starting point. Picking something smaller than 1, like 0.2, is going to be a wider parabola. I'm going to have this be 0.2 x squared, for example. And then, of course, we can do even a third graph here. If I were to make that y equals negative 0.2 x squared, the same thing we had said a moment ago about negative numbers is still true. It's going to be wider because of the 0.2. It's just going to be facing downward because now it's negative. So to practice using all these wonderful observations you noticed in that first part, there's this question here on the screen. It's pretty much like what we did on the warm-up, except now it's quadratic equations. You have 3 quadratic graphs and 3 quadratic equations, and your job is to match each equation to the graph that represents it. And then also the second part of this is identifying in the equation how you are using those different terms to help you identify which graph correctly matches it. Go ahead, pause the video now and try this problem. Come back to see how you did. I'm going to do both of these questions below simultaneously by going through each of these equations and identifying what each term in the equation tells us about the graph. Starting with the very first observation, which was about these constant numbers I see. We learned in that first observation that the constant lets you know the y-intercept. So for this first equation, that -4 tells me the y-intercept would be at -4. The 1 tells me the y-intercept is at 1. And then that +4 tells me that is our y-intercept. Oops. The other part to this is what those x squared terms are telling me. We learned in this lesson that the number in front of x squared can tell you a lot. If you have a number bigger than 1, it tells us it's more narrow. If you've got a number like 0.5, 0.3, those numbers less than 1, it's wider. But notice here, I don't have any actual like coefficients. All we have is a sign, and that's what we're using in this part. Because this x squared is positive, that means it faces upward. Because this x squared is negative, it faces downward. And again, because this one is positive, it faces upward. And that is what we're using to match these graphs. Notice over here, there's only one that goes down. And so graph C must be g of x. It has a y-intercept at positive 1 and faces downward. And so C is, I'm just going to do it this way. C is our g of x. For graphs A and B, those both face upward, so it's really those y-intercepts I need to use. Graph A has a y-intercept at positive 4, and graph B has a y-intercept at negative 4. So since B is at negative 4, it must be my f of x, and that leaves graph A must go with h of x. So notice, in order to know this, it's not just enough to know if it goes up or down. You need to know all of our observations to help you identify which one is which. I do know for a fact that there are homework questions like this where you're matching graphs to the equations, and there also might be a test question in your future similar to this. I really like this question though because it's using a combination of observations, and it also is really similar to how we started this lesson with the warm-up. There is one final part to this lesson, and that's what we're going to look at next. This is the final part of this lesson, and I love this because it's a good old matching activity. We're going to be matching multiple things together, starting with factored form and standard form. Up here at the top, I have 3 different equations in factored form that we are going to be matching with these 3 equations below in standard form. This is the lesson we had worked on 3 lessons ago, where we talked about what can you do to change factored form into standard form. Will you do the multiplication? We had talked about 2 different options. You could use that diagram or that box to help you do the multiplication, or you can use distributive property. It is up to you how you want to do it. But go ahead, pause the video here for this first part and see if you can identify which one should match together. Come back to the video when you think you have an answer. I'm going to do this first one as an example, just as a reminder in case you need it, and then put up the answers for the last 2. This first equation, if I wanted to figure out what this is in standard form, I'm going to go ahead and show the distributing method. If you do the diagram, you're going to do all same 4 multiplication problems. So with distributing, I'm going to start with that 3, and I'm going to distribute it to my other parentheses. I'm going to do 3 times x and 3 times negative 1. Be careful with the signs, especially on this one. So 3 times x is 3x, and 3 times that negative 1 is negative 3. And then I'm going to do the same thing with my second term. That's a negative x right there. So I'm going to do negative x times x, and negative x times negative 1. Negative x times x is negative x squared, and negative x times negative 1. Negative times negative is positive, and x times 1 is just x. So we get these 4 terms here. The last part is simplifying this. I see there is a 3x and an x that I can combine together. And when I do that, 3x plus x is 4x. And I'm going to copy everything else. So I've got a negative 3 and a negative x squared. And after doing that, it's easy for me to see it is the second one here. I'm going to go ahead and move that under this one. The other 2, like I said, you can use distributing or you can do the diagram option. This is going to be the answer for that one. And then this is our standard form for that factored form. This is the first part of our matching activity. The second part of our matching activity is going to be matching our intercepts with these functions here. So we've got 3 equations, just 2 different ways of looking at them. And you're going to be matching that information with these x and y intercepts. In order to do this, there's some things we've learned in the last 2 lessons that are going to be helpful to remember. If you want to find your x-intercepts, we said one of these is going to be more helpful. To find your x-intercepts, what should you be looking at? You want to look at factored form. And then what we learned today, we've been looking at standard form, and standard form is going to be more helpful for your y-intercepts. For y-intercepts, you want to look at your standard form. And so that is what we're going to be doing in this next part. Again, go ahead, pause the video. Remember, getting this practice is super important. You want to make sure you're practicing before you go on to the homework and the tests. Pause this video here and see if you can match these intercepts with those three functions. All right, I'm going to start with standard form and y-intercept because that's what we were practicing in this lesson. We learned that if you are looking at standard form, that very first observation we made is that the constant always tells you your y-intercept. So looking at this standard form right here, my constant, that number by itself, is -3, and so that must mean the y-intercept is -3. Looking at standard form here, our constant is 4, so my y-intercept must be 4. And then for this last one, there is no constant. There is no plus or minus a number. And so no constant means the constant 0. It must mean it's plus 0. And that means our y-intercept is at 0. Now for this matching activity, that was enough information for me to do all of the matches, but I do want to still practice and confirm all of these with the x-intercepts. We had said earlier, x-intercepts are easier to identify looking at factored form. And remember, the way specifically we were doing that was we were setting each part of factored form equal to 0. We were setting 3 minus x equal to 0, and we were setting x minus 1 equal to 0. When you do that, here you're adding x on both sides and you get 3 equals x. Here you're adding 1 on both sides and you get x equals 1, which is why those x-intercepts are at 1 and 3. Similar here, if you set x minus 1 equal to 0 and x minus 4 equal to 0, you get a positive 1 and a positive 4. Here, x minus 4 equal to 0 gives you that 4 again. And then here, we're just setting x equal to 0. So x equals 0 means x-intercept at 0. The final part to this is going to be using all of this information we've identified, factored form, standard form, x-intercepts, y-intercepts, to match it with these three graphs here. One final time, I'm going to ask you to pause the video, use everything we've learned in today's lesson and the past 2 lessons on graphs of quadratics to help you identify which graph represents each of these functions. When you think you've matched them all up, come back to the video to get the answers. So there's a lot of different ways to match these up, but I'm going to start with what we learned in this lesson about standard form and then back it up with some of the stuff from previous lessons. We learned in this lesson that when you have standard form, that constant is going to be your y-intercept. We've already identified that. And then we've identified that that x squared term is going to tell you if it's narrower or wider and if it's facing up or down. So looking at our 3 standard forms here, the x squared is negative, so that means it's facing down. And then here and here, x squared is positive, so it's facing up. Just by knowing that helps me know the only graph that's facing downward must be our first function. I can confirm it by checking these other things. Notice the y-intercept is here at -3, and then we have x-intercepts at 1 and 3 as well. Similarly, both of these are facing up, so that is not enough information, but I can use some of this other information to help me identify which one is which. We see here the constant is 4. We said the y-intercept must be 4, and so looking, that must be this red one. And then the one with the y-intercept at 0 is going to be this final one. Again, I can double check just by looking at my x-intercepts, 1 and 4, x-intercept 0, 4. Yep, it's looking good. I love this question here because you're practicing using so many different things that we need to know from this unit. And what we're doing in tomorrow's lesson is all of the same stuff, identifying intercepts, looking at graphs of quadratics. It's just all going to be based on real stories and how we can use all of this to help us analyze the story. So this is great preparation for our very last lesson. Thanks so much for watching, and I'll see you in the last one.